Chapter 3, Differentiation. We will look at section 3.2, the derivative as a function. If you will recall, in chapter 2, in the first part, we looked at the average rate of change of a function over an interval, say in this case from x of 0 to x of 0 plus h. So the width of this interval is h. And then we said that the average rate of change over this interval is equal to the slope of the secant line that joins these 2 points. See, when x of 0, then your y is, of course, f of x of 0. And of course, when you skipped, you jumped a step, a width of h, then this is x of 0 plus h. The corresponding y value would be f of x of 0 plus h. And the x coordinate is, of course, x of 0 plus h. So this black line, the secant line that joins these 2 points, has a slope of change in y over change in x. And it's just really this function without, this expression without the limit. But now if we get this h, if we let h approach 0, which means x of 0 plus h is going to scoot down and get as close as possible to x of 0, that's when we have a limiting effect and we get the slope of the line tangent to the curve at point P. So if this happens, if we can always generate a slope at every point, okay, at every point on this curve, then what we derive, in fact, is a derivative function. I will show you this quick applet just to see how it behaves, how the secant line evolves into a tangent line. So what I'll do is I will move this point right here at where we want to create a line tangent to the curve. This is the graph of the cubic function y is equal to x cubed. And if we do a very slow motion or speed of it, then once I press display, what's going to happen is this blue, the secant line, which is the blue dashed line, is going to eventually coincide with the line tangent to the curve at this particular point. So let's press play. There you go, and see how the slope of the secant line changes as it scoots from this point. See, as it scoots from this point going to this point. So let's do that again. Press play. There you go. So what happens is the slope of the line changes each time at every movement that it takes to start from this point going down towards the tangent point. All right, so that's how you've seen. Suppose we want to look at x squared. Let's see how an x squared looks like. Okay, here we've got a secant line, and as you can see, if I don't move this right here, you'll still see how this secant line is going to evolve into the line tangent to the curve right there. Okay, so let's do that again, and I'll move this a down to the same point, and let's see how the secant line, see, the slope will change each time it moves. Every time it moves, the slope of the secant line changes until it becomes the slope of the line tangent to the curve at the tangent point. Let's press play. There you see it slowly scoots into the tangent line. So let's go ahead and define the derivative of a function. So the derivative of a function f of x. Now this is very important, this phrase, with respect to the variable x. Like, this is a function that's acting on x. So with respect to the variable x is the function f prime, whose value at x is, like we said, it's the slope of the line tangent to the curve at x. So it's this secant line, the slope of the secant line, and then we let h approach 0, then it becomes a slope of a line tangent to the curve. So It says here that if this limit exists, then that's the derivative of the function at x. Now, some of the notations that for the derivative of y equal to f of x is sometimes they use f prime of x, y prime, dy by dx, d by dx of f of x, df by dx, and sometimes they even use this capital D subscript. So this means the derivative of f with respect to x. If y is equal to x squared, this is an example of how we will apply the definition. Okay, show that y prime is equal to 2x using the definition of the derivative. Let's start. Y prime by definition is equal to the limit of f of x plus h, okay, and then minus f of x. This whole thing will be divided by h, and then we let h approach 0. Okay, so now let's apply the function f of x plus h on y is equal to x squared. So that's equal to the limit of x plus h, whole thing squared, then minus x squared, divided by h, and then we let h approach 0. Okay, and then of course we just work that out. Remember, we want it to be equal to, in the end, equal to 2, y prime to be equal to 2x. So what's that going to be? We take the limit of, that's x squared plus 2xh plus, of course, h squared minus x squared, whole thing will be divided by h and let h approach 0. Okay, look at a few terms that will cancel out here. X squared and x squared will be canceled out. And so what's left on the top? It's equal to the limit of, let's see, that's 2xh plus h squared, whole thing divided by h. And then, remember, we have a 0 over 0 here, so we see if we can pull out what makes the numerator and the denominator equal to 0. So let's go ahead and factor out h. It's equal to the limit of h times 2x plus what? Plus h, whole thing divided by h. And we are lucky that there we can cancel the h. This is equal now to the limit of 2x plus h. And remember, it's our h that goes to 0, not the x. So with respect to h, that means 2x is a constant, so only h goes to 0. So the limit of 2x as h approaches 0 is, of course, just 2x. Therefore, we have shown that y prime is equal to 2x. So the slope of the line tangent to the function y is equal to f of x at, say, x equal to a is letter m, as we always use letter m. So it's now equal to what? It's f prime, and instead of plugging an x there, we substitute the value of x equal to a into the derivative function. So it becomes f prime of a. And what is f prime of a? That is the slope of the line tangent to the curve at y equal to f of x at the particular point when x is equal to a. Now let's see. Here we have an example. If y is equal to x squared and y prime is equal to 2x, the slope of the line tangent to the graph at, say, x equal to 3 is what? That means we substitute x equal to 3 into the slope function, and that means that the slope m is equal to 2 times 3, which is equal to 6. Now, how does that look like? Well, why don't we graph the function y is equal to x squared? Okay, we have x equal to 3, which means y is equal to 9. So there's the point, and here we see the blue line shows the line tangent to the curve at x equal to 3, and the slope of that blue line is equal to 6. Now let's observe too what about in other points of the graph of y is equal to x squared. So let's plot the graph of the function y prime. So that's just a straight line with slope equal to 2. So when x is 1, y is 2. So So we see that we just have a straight line passing through the origin with slope equal to 2. Now, how does this relate to our original function y is equal to x squared? Say, suppose we take a point to the left of 0, say at that negative number of x. We have that the slopes of the lines tangent to the curve to the left of 0 are all negative. So you see all these lines that are tangent to y equal to x squared are negative, and then it becomes 0 when we hit the vertex, because the slope of the line tangent to the curve there is 0. And then past 0, when x is greater than 0, we see all these lines tangent to the curve that are positive. We have all this positive slope, and of course, you know, our example m equal to 6, that's positive. Now if we plot all those points, these points that we have here correspond to the points, or these slopes that we have there correspond to these negative slopes. All of these values of these slopes, they correspond to every point on the line y is equal to 2x, where they're negative. And of course, when it passes through the origin, that's when the slope of the line tangent to the vertex is 0, so it passed through the origin. And then, okay, see, when x is equal to 3, remember y prime is equal to 6. That matches the slope of the line tangent to the curve at x equal to 3. There we have y prime equal to 2x.